Good. So it looks like the 5 minutes are over. Very fast 5 minutes, indeed. And we continue. So I would like to start the second part of the discussion with the thermodynamics of dust. Because dust, I think, is extremely important. We've seen it can provide shielding for certain species. Why? Because it absorbs radiation at high frequencies that can affect or destroy molecules or ionize atoms, but it re-emits this energy as thermal radiation at infrared wavelengths typically. So dust acts as a thermostat and it redistributes the energies, the frequency distribution of your radiation. It turns out that dust temperature is very, very insensitive to the radiation field. We talk about a square root of 6 dependency. So you can vary the radiation field by a factor of 1,000,000. The dust temperature would only change by a factor of 10, roughly. That's very, very insensitive. So it acts, in some sense, as a thermostat in the interstellar medium. And because gas can collide with dust, some of these thermostat probability or abilities or Eigenschaften, properties are then given to the dust also. So above a certain density, as we have already seen in these temperature density diagrams, the gas gets coupled thermodynamically to the dust. So how does this work? Let us first look at the radiative heating of dust. So dust is heated by the absorption of radiation. So I take the number of photons times the speed of light times the energy carried by the photon times some kind of absorption coefficient. This is the classic way you take basically a pipe, you send photons with the speed of light, and you're asking how many of these things are absorbed. If your absorption elements are sparsely distributed, you can simply add up their cross-sections. They're not overlapping. So this is the entire assumption. You notice you can also, here's the intensity of radiation. This cancels out. I just have written it here in the sense that this is the number of photons at this frequency bin with this intensity. Okay? And one needs to say, what is the absorption cross-section? So this is the geometric cross-section here. Pi times the effective radius of your dust, but we have seen dust is fluffy, fractal, whatever. So there will be a frequency-dependent effective factor, this QS. And it turns out that this QS, the absorption Q, the effectiveness, divided by the radius of the grain, has a strong frequency dependence. So this is the inverse wave number, low frequencies, high frequencies. The absorption coefficient gets very large at high frequencies. So this is the reason why dust absorbs UV photons very efficiently, but not so efficiently in the infrared or at radio wavelengths. You can then average over all the frequencies to get an efficient or an effective cross-section, and then you have the average absorption energy change as this effective absorption efficiency times the geometric cross-section times the energy density times the speed of light. So you see again this depends sensitively also on the size of the particles. Good. So what is now the size distribution? The larger your grains, the more efficient the absorption is. However, typically you're dominated by small grains, but they are much more abundant than the big grains. So this is why typically the opacities are then dominated by more the smaller scales. So typical values, one needs to distinguish between silicate-dominated dust and graphite dust, which is created by different processes in the in astrophysics, they have this scaling dependence. And so basically, it is well fitted, this empirical and experimental curve, by these power law behaviors here. That helps you if you want to calculate simple rate coefficients. Good. That was the way you heat the dust, the gas. No, the dust. Now it's the question, how do I couple between gas and dust? And you can again define a net energy transfer rate that knows about the kinematics of the gas particles. So this is something like the RMS velocity of the gas particles. Again, here we have the cross-section of the dust thing. There is an efficiency factor. I come to that in a minute. And then there is simply the difference of the temperature. So if the gas is hotter, then it gives energy to the dust. Dust provides cooling. This is the case typically in interstellar conditions. However, you could say I have a dust enshrouded protostar. So a protostar that sits in a dense envelope. The protostar shines, heats up at infrared wavelengths the dust, and then this would be a typical condition where the dust temperature is larger than the gas temperature, and it provides cooling to the gas. So what is this efficiency factor here? It measures the efficiency of the energy transfer. So if we have a fully elastic condition, no energy is exchanged. So this is no good. We want inelastic conditions, and apparently it turns out that even if in this interaction, in this collision, the molecule or the atom sticks for only 10 to the minus 12 seconds on the dust surface, this is enough to exchange energy. Then we put alpha equals to unity. And of course, I need to sum over all the species that I have available. These are the i's. So different gas species. And I should also note there is not a 3/2 k, but a 2k, which takes case of the fact that warmer particles move slightly faster. So you can plug that in a typical box calculation. Yes?
So just what does the dust temperature mean there, since the different grains have different temperatures and size? Are you summing over this also, or is it some sort of mass-weighted dust?
It's some miraculous average mass-weighted thing. I do not want to complicate issues too much. I say my dust has a temperature, basta. Now, in principle, you would need to evolve dust also, and you would do that for different size distributions. So what we do in reality or in our calculations, which hopefully mimic reality, we take the typical solar neighborhood dust properties, size distribution, composition, put everything into a big program, integrate, and get out with a dust temperature. So these are all integrated quantities, if you wish. So we refer to the people who did this integration and gave them numbers, which we can plug into our chemistry. So this is the result. A recent paper in preparation by Paul Clark and Simon Glover. This gives, again, density and temperature. This is the dust temperature, the blue thing, and the, what is that, orange stuff is the gas temperature. And these are three different cases. This is the average interstellar radiation field. Remember, this is 1.7 times the halving field. This is 10 times larger radiation field. You see the dust is slightly hotter, but not by much. And this is just the standard interstellar radiation field, but now the metallicity is slightly smaller by a factor of 10, and you see it changes the coupling. So you notice dust is insensitive to the radiation field. What we also notice is that at some density, no matter what you do, is dust couples or gas couples to the dust. And this depends. The density where this depends on the metallicity. So here it happens earlier at solar metallicity. It happens at higher densities later for reduced metallicities. once the gas couples effectively to the dust, you can form H2 efficiently on the dust grains. This releases latent heat that can heat the gas. So this bump is due to H2 formation heating and can be significant here. The third thing to notice is that altogether the interstellar medium is far from isothermal. So if you want to get the dynamics right, you need to have a handle on these various heating and cooling processes. This is just one out of a zoo of many, many, many. Good, that was an application. Let us now go to the radiation. Now, the emissivity, the energy change due to emission, again, you can say it radiates thermally, the Planck spectrum, 4 pi, so it radiates isotropically, and it is informed about the absorption coefficient. I think that should be a Q. You can then say, well, let us say it emits thermally, so I can solve for this integration. I introduce an effective absorption coefficient, and I express the energy density that I have in the Planck function by the Stefan-Boltzmann law, so it goes with the dust temperature to the 4th power. This is the definition of the effective absorption coefficient. It is the so-called Planck averaged emission coefficient. So whenever you do these averages, you want effective quantities, effective absorption. You can do Planck averages, you can do Rosella mean averages, etc., etc. The good thing is this can be, as we have seen before, approximated by a power law with respect to the frequency or the wave number. So you can plug all these together, and for specific dust species, this would be a good formula to use. Now, this is to elaborate. When you actually use it, you rely on other people's work that tell you the effective absorption coefficient scales for silicate dust with this proportionality factor and this size distribution with the wave number to the -2 wavelength. This gives me an effective absorption coefficient, and I can measure that. This is my approximation, and in this temperature range for silicates and graphites, it's working quite nicely. So I have now absorption, I have emission on the other side. I do what I have done before. I look at the detailed balance. In equilibrium, this gives me a handle on the dust temperature. So thermal emission balances radiative absorption. This is typically, let's say, a stellar spectrum, peaks in optical ultraviolet wavelengths. This is typically a thermal infrared spectrum. So we can plug in the numbers, this dependency with beta something like 2. We can solve that. We get this equation for the steady state solution. This is taken from Bruce Drain's book. I have it here. Again, an excellent book. If you want to look at it, I keep it here. The other book I've been using in preparation is by Xander Thielens, also a very good book on the physics and chemistry of the interstellar medium. And what is the result is you see that the equilibrium temperature depends to the radiation field to the 1/6 power. So extremely insensitive. One can try to measure that, and indeed you can change the intensity over many orders of magnitude, and the dust temperature only rises by very little. And these are the numbers you would like to plug in for silicate dust and carbonaceous dust. So I just provide this here tabulated. So there is one note I should make. This was all integration. Effects like elasticity do not appear. Which is fine for large grains, because they have lots of thermal inertia. If a photon hits a large grain, it's just an epsilon effect. Its temperature with absorption is it's almost constant. However, if you go to smaller and smaller grain sizes, the thermal inertia becomes smaller and smaller. So once they're hit by a photon, they become really stunned and suddenly change their temperature and their thermal energy content enormously. So you get in a regime where the heating is stochastic, right? You have temperature spikes, it decays again, comes another photon, etc., etc. So this you should take into account if you talk about heating processes and chemical processes on very small grains. And usually this is not be done. Usually you just integrate and say, oh, effectively I then absorb a fraction of a photon, which is not the right thing to do. Good. Let us then go to the dust cooling, to the gas cooling processes. Yes?
So my question is about the spin of the dust.
Yes,
If there's
spin.
a magnetic field,
Mm-hmm.
then your radiation shoot into dust, then you get the spinning,
Yes.
you get the emission. So does anyone try to consider about this part?
Yes, so in my simple presentation of literature knowledge, I have completely ignored this effect. But when we talk about dust polarization, it's all about that things. So if you do dust polarization, you need to go to the Stokes parameters. So you need to decompose your intensity in the 4 Stokes parameters, which is a full-fledged, vollständig. So it's a full decomposition, you can do that. So you can do then your radiative transfer, not just in the intensity, but you can do it in the Stokes parameters. And it adds another level of complication. So you play tomorrow with RAD-MC. RAD-MC has now capabilities to do that. And if you want, you can play with that. But I will not go into further details in that, because it is extremely complicated. It's, I think, just starting. It's just at the beginning that people do that properly. And to polarized radiative transfer is very difficult. I wish I could do it, because then I could do beautiful polarization maps of, let's say, our outflows and stuff like that. But we're not there yet. Good. So gas cooling typically relies on transitions. And we have electric dipole transitions. They lie typically in the UV and optical, but we can also have rotational or vibrational transitions. Right? Electronic transitions is you take one of the outer electrons, put it from the ground level or some low excited state into a higher excited state. Because their electronic transitions, typical energies are of order of electron volts. Vibrational, the entire, let's say, carbon monoxide oscillates with respect to each other. Typical energies are 1/10 to 100th of an electron volt, and the rotational transitions are the one that have the lowest energies. These are typical oscillator strengths. You see these are very efficient, very effective. These have very little oscillator strengths. And this is the corresponding Einstein coefficient for a generic case, and this is just an example, CO for instance. Now, often the electric dipole is not allowed, then you still can have forbidden ones. Electric quadrupole, magnetic dipole, fine structure lines, hyperfine structure lines, etc., etc. So there's more beyond simple electrons. There are selection rules. The most important one is that the spin angular momentum need to change by ±1. And 0 to 0 is not permitted. Typical examples are, let's say, the hydrogen transitions. Lyman alpha goes back to the ground state. Then there is the Balmer line that goes to the n equals 2, Paschen n equals 3, etc., etc. This gives rise to this well-known term diagram, and you see all these lines. And Lyman alpha is very important, we have seen in the Lyman alpha forest in the high redshift universe. The vibrational transitions are a bit more complicated, because now we are in the realm of molecules and not simple one atomic, or effectively one atomic electron approximations. What you do is you see that this is the energy surface as function of distance, and there's expulsion, there is the separation of the two components of the molecule, and in between you have these vibrational lines and transitions. You see, this can be approximated by a harmonic oscillator around the minimum, and this is just the energy levels of an harmonic oscillator from quantum mechanics, well known. The transitions are then simply going from one level to the other one, and all transitions, say 1 to 0, 2 to 1, 3 to 2, etc., have the same transition energy. It's just a difference in energy. So delta V of 1 is the fundamental transition, but you can have the first, the second, etc. overtone transitions. Now, if you have diatomic molecules, they're simple because the things can just vibrate. But if you have three things, they can vibrate like that, they can vibrate like that, they can vibrate like that. So you have all hell can break loose. And this is just a picture of where the different components, let's say a CH component, where potential vibration will sit. So it is not necessarily that the entire molecule vibrates. It is okay if just one bond starts to vibrate. So this can get extremely complicated. Again, for simply rotational transitions and simple diatomic and linear molecules, the rotational levels simply depend on the rotational quantum number J. So this is the Planck constant, and this is the moment of inertia. And the moment of inertia, to a good approximation, is simply the distance and the mass of the two molecules. And you can, one of the questions in the tutorials tomorrow is, why is there a slight difference in the frequencies of the isotopomers of CO, let's say 12CO or 13CO or C16O and C18O, etc., then this is probably reason to look for. The statistical weight, again, depends on the rotational quantum number. The selection rule tells us that delta J must be plus minus 1. So again, this gives a very simple spectrum. It scales linearly with the rotational quantum number, right? The transition energy. So this leads to a rotational ladder. Let's say for CO, these are the first transitions, and tuck, 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 tuck. It's very simple to identify. And this is just tables from Xander Thielen's books of the various transitions, the transition frequencies, the energy associated, the Einstein A coefficient, and the critical density for this line to be excited. Now, typically, you can combine all of these transitions. At least the rotational and the vibrational transitions are in the same energy range. So you have an energy, a difference of the state that now depends on V and J in such a way and gives rise to this very complex spectrum. Good. These are just examples what other transitions are available. And I go quickly over that. So now we have electronic, vibrational, and rotational transitions. Now, how can we, using that stuff, cool the material? So in order to cool the material, we need to go back to our radiative transfer, and we go back to the simple system. We know the two-level system. So let us assume we want to calculate the cooling power that is provided by a transition that goes from I to J. Again, in the two-level approximation, I would be 2 and J would be 1. So it is custom to write these in terms of density squared times this cooling function for the species X for this transition A to J. And how is this calculated? So there's certainly the density of the species I, the transition, or the level, the density of the level population of the species X in level I. So this is now correct. The absorption coefficient, the energy, this one is the escape probability. It tells us, is the photon that I emit being reabsorbed in the vicinity, or can it escape the system, right? I can only cool if the photon can escape. If I'm in a very optically thick regime and the photon gets absorbed by my neighbor, I can't cool at all. So this is an important quantity and it is difficult to calculate. And then here I look at the ratios of the emissivity and the background radiation field. So this is the, for dust, let's say, or for other things, the emissivity in this frequency band. And this informs me about the background radiation field. And typically, it has maybe a few components. One would be the cosmic microwave background. It is the emissivity due to dust, which is a thermal emission. And if you're in the vicinity of a star, you would add contributions of starlight. So the source function, again, needs to include the statistical weight and the population of the levels. Here's the frequency, here is the speed of light squared. So we do what we have done before. We assume that in statistical equilibrium, the reactions that populate a level are equal to the number of reactions that do depopulate the level. So you notice that it looks very similar. I have level I populated, and I need to sum up over all transition probabilities from A to K. I sum up over all, let's say, levels I can reach. Of course, I must include myself. And then I ask, if I start from level K, what is my probability to reach a level I? So here you sum over nk times rka. So these are the forward, the loss reactions, and these are the backward, the gain reactions. Oh, this should be K. K, oh, no, that's right. Good. Now I can say, well, the simple Einstein approach, where he puts his two-level or multi-level system into a radiation field, needs to be extended by collisions. So I can excite and de-excite by radiative transitions and by collisions. So this is the radiative part and this is the collisional part. So in what follows, C are collisional rates and A are the radiative rates. So here again you have something like an effective transition probability. Here you have the escape probability. And you need to take care whether you go down to lower levels or whether you come from lower levels and go up. Good. Now, this needs to be coupled to the ambient radiation field. So the QIKs you have seen before now needs to be informed about the ambient radiation field. It has this prefactor, and most of the complexity of the problem is here, because this makes it a non-local thing. Because the radiation field typically needs to be informed by the photons that could become from everywhere, from all the other regions in your computational domain. So chemistry is intrinsically local, but when it is coupled to the radiation field, and it usually is, then it becomes very non-local. And much of the efforts to solve for the chemistry are dealing with making it local again and getting rid or making local approximation for the radiation field. So the equations you have here, these guys, these n equations, are not independent because they must fulfill a continuity equation for the species n. So if I sum over all levels of the species x, then I must get the abundance or the number density of these species. And as we shall see later, because I have one more equation than, I have one more constraint than equations, I can run into troubles here. Good. Let us now go back to our simple two-level system. And let us start with optically thin conditions. So I put my escape probability to unity. Every photon I produce escapes my system and contributes to the cooling. And I say I have no ambient radiation field. So I look at collisions that populate the level 2, collisions that depopulate the level 2, and they compete with radiative transitions, right? N is the total density here. Detail balance again tells me that the forward and the backward reaction are related by the transition energy and the statistical weights. So that I can use to get the ratio of the populations, N2 over N1. We have seen that before, but now collisions do the job that we had the stimulated and emission and absorption. And what we can do now is we have a competition between the collisional de-excitation and the radiative de-excitation. And it turns out that the rate of these two coefficients gives me something like a critical density. If I'm above this density, I should say this can easily be extended to a multi-level system, right? I just need to look at all downward reactions, and collisions can also occur in higher energetically higher states. So the sum here goes over all possible states except my own, and this goes only over states that are below my own. So notice that there is a difference between the radiative transitions and the collisional transitions. Good. So if the density is larger than this critical density, the de-excitation process is dominated by collisions. So typically you have beefed up by hard work your atom or molecule in the excited state. It is eager to emit a photon, but then it gets bumped in again by some collision partner and gives away its energy. So this is not good for cooling. So here we have the system is then in local thermodynamic equilibrium, and the temperature that defines this equilibrium is the kinetic temperature of the gas. So it is the collisions that know about the kinetic temperature of the gas or whatever you deal with that enter these equations here, these things. Good. If this is not the case, if you are below this critical density, then typically radiative de-excitation dominates, and we have a difference between the radiation temperature and the gas temperature. So we are not well coupled. This is the non-LTE case. So the excitation temperature can then be defined by that, and we can combine this one with that one. So the level populations here, definition of the excitation temperature. And this gives us a ratio between the gas temperature and the excitation temperature. So kinetic temperature of the gas, temperature of the radiation field. And this is an effective temperature because typically we do not have a Planck spectrum where the temperature is well defined. Good. So even if this is the case, for that, we still get comparable excitation temperatures in the gas temperatures. But it should be said that in this case, the upper level will hardly be populated. So this is not really relevant. Typically, when you are above the critical density, then the excitation temperature is the gas temperature. If you're below, then typically the excitation temperature is much below that. Good. We are not done yet. Yes.
Is the previous slide equation, is the limit right?
There could be that it's wrong.
Because if the critical density is very high, then right-hand side of this.
You mean this one or this one?
The upper one, for high critical density.
This one? if you're at high critical densities, you collide a lot, and then
I'm sure, but looking at the equation, if the critical density is really high, then
Here.
the third equation on this slide, so just above
This one.
Yeah. So if the critical density is very high, then the logarithm is very large.
oh, you mean this and this does not fit together? Oh, the critical density is. So this is small. I have this is 0. This is
No, it's the other way around. The critical density is very high, so critical over
yes.
that becomes large, plus 1, it's still large.
Ah, okay. So this is a large thing. So this is. So this is a large factor. Then we need to ask, what is this thing?
Yep.
If this is small, then this can compensate this large factor.
Yep.
So typically we have that the excitation temperature is much smaller than the gas temperature because this gives a large factor if this is of order unity, say. But I can eat away this large factor by going to very small temperatures, then I still can make this to 0, and I have roughly unity
Yeah,
here.
that's your bottom statement, right?
Yes.
Yeah, but if you go 2 statements up,
This one.
yes, that's the one that works.
Oh, I see.
So if you take the limit in the upper right equation, n2 over n1, then you get a reasonable answer.
Yes.
Yes.
Here. Then this. Right.
Take the limit there, then plug in the laptop.
Yeah.
Yeah.
Good. Thanks for the help. Good. Now we need to calculate the rates. So in order to calculate the rates, you have here some, this is the how is this called? The reduced mass of the system that you encounter in collisions. This is the temperature, so this is just the Maxwell-Boltzmann factor here. There is a cross-section, velocity squared, and there is the Maxwell-Boltzmann factor of the velocity. So the question is, what is then the collisional cross-section? And often it depends on the relative velocity. This often turns to be a square root dependent on the temperature. Typical values you can then integrate over all velocities are given here in this table for neutral, neutral, electron, neutral, and electron ions. And you see here you have a strong density, temperature dependence. Here this is not so much the case. Now we can go to the equation we had before and plug in what we had, right? The cooling rate, and we end up with this expression here, where we introduced now the total density and the fraction of the species is given by the fractional abundance here. Again, for high densities, we obtain local thermodynamic equilibrium as expected before. In the low density limit, we expect that every upward collision results in the emission of a photon, and the cooling strength scales quadratically with the density. Here we have a linear scaling. So in this regime, we can simplify that to this expression, which is often used. Density squared, fractional abundance, this, it was on the previous page, the collision coefficient times the energy. Good. So I can go to a system which now has optical depth. And I do that first for the 2-level system because that makes things easier. So I have now 4 terms in the equation: collisional excitation, radiative excitation, so absorption, collisional de-excitation, and then comes the Einstein stuff, spontaneous emission and stimulated emission. And you notice this is now a strongly, strongly coupled non-linear system because the radiation field is a non-local problem. So we need to calculate in order to calculate the level populations, we need to solve the radiative transfer problem. In order to solve the radiative transfer problem, we need to know the level populations. So it's a chicken and egg problem that we need to solve iteratively, or we try to make smart approximations that may work in some cases often they do not. So what are these simplifications we can do? We can say, I try to make this local, I define a local escape probability. This is also called often large velocity gradient in its most simple form, or also called Sobolev approximation by the guy in Russia who did the same thing. Also, we assume that the local level population also holds globally. So if these two assumptions hold, we have now decoupled our system from the radiation field and it becomes local again. So why is that the case? Let's say if the net number of photon absorption events that we correct for stimulated emission is equal to the number of photons that do not escape the local volume, then we have a sub-equation for detailed balance. That is this one. So number of photons absorbed corrected for stimulated emission is equal to the number of photons that do not escape, 1 minus this beta parameter times the absorptions. Now we can go back to the previous equation, to this one, plug in that one, and we see that this term and this term cancel with this term in some sense. So the full local equation that we get, which has no longer a dependency on the radiation field, is this one. We have that seen before, just that we have now this escape probability. This is why it's an extremely important concept. We recover the same formal solution for the level populations like that, only that now our critical density is not just the ratio of the radiative and the collisional coefficient, but it is weighted, if you wish, reduced by the escape probability. So this effectively lowers the critical density for reaching LTE, because not all the photons escape, a few are re-emitted. Now, how do we calculate this thing? Because here all the physics is, and make a Gedankenexperiment. Let's say you look at photons that come from a layer like this, but the layer has a line of sight velocity gradient. So just like that. The photon is emitted in a line with a certain frequency band. Now, it cannot be absorbed if I Doppler shift away the line that is emitted from the absorption line, if you wish, sufficiently enough. So if the absorption line and the emitted line are fully overlapping, the photons get absorbed again. But we have a velocity gradient, so stuff that is emitted here may not be absorbed by a gas particle that sits here because I have the Doppler shift. The lines only overlap in the line wings and the absorption coefficient can be minute. So we can write the corresponding optical depth like that, but we have a new parameter that is now the velocity gradient. So if you just shift large enough, I shift away my frequencies. And for simple geometries, I can calculate it analytically. This has been done here for slab geometries, but you can also do it for spherical things, and you find in the literature then approximations for these. And in this case, the tau equals 7 gives you two different formulae. Good. So how am I doing in time?
I think you have something like 10 minutes.
Okay. Good. Let me then rush through the actual cooling processes. So what we have discussed so far is, if you wish, the mathematical theoretical skeleton. Now we need to put life into this formula we have derived. We need to look at the cooling processes in different phases of the material. So let us start with cooling in ionized gas. Typical temperatures are 10,000 Kelvin. And what we see is the important or the dominant cooling mechanisms is the exciting of low-lying electronic states of, say, the O2 emission or the O3 emission and N2 emission. They're excited by collisions with free electrons in the ionized gas. So that tells you that later on the ionization degree is very important in driving chemistry. And this is the collision strength, again the statistical weight. And these are just typical numbers. You can look at tables for your favorite transition and you have these collision strengths. So this is a typical table I took from Xander Thielen's book. You get the transition velocity. This tells you in this spectroscopic notation which orbital this transition is taking place of, the energy, the radiative coefficient, this thing that we have discussed before, this collision strength, and the critical density. You have everything to plug it in here with that and with that, and you get the cooling. Now, you can do the same for atomic gas, and it turns out that because the temperatures are much lower now, the cooling by fine structure lines is very efficient, but it has no temperature dependence. Indeed, we also need to distinguish between what excites my transition, whether it is a collision with hydrogen, so atomic hydrogen, with electrons or ions, or with molecular hydrogen, if you are at very high densities, so at the basically in a photodissociation region, almost in the molecular phase. Example for C+ cooling, I've shown you before, you get such a cooling rate. So fractional abundance, no, this is the, so we assume it's fully ionized, and this is the ionization degree of H of hydrogen. So because this provides most of the collisions. So ionization degree of hydrogen, we assume carbon is fully ionized. This is the fractional abundance of the carbon, and it gives me this energy dependence. We see that often it is an exponent of some critical temperature divided by the actual temperature. And the result is ergs per cubic centimeters per second. It could be that optical depth effects become important, so we can calculate the critical column density for tau equals 1, the transition to optical thickness, and typical numbers are 7 times 10 to the 21. You see that this is equivalent roughly to where dust shielding and self-shielding of H2 becomes important. So these lines are not fully optically thin. We need to do proper line radiative transfer in many cases. And again, the table from Xander Thielen's book with proton collisions and hydrogen collisions. And the resulting cooling curves are like that. So you've seen that before. Temperature here is the cooling strength, and this is the total value. And I sum up over the contributions of the C+ line at 158 microns, the atomic oxygen, the silicon plus line, etc., etc. Lyman alpha kicks in at higher temperatures, temperatures. This is now for an ionization degree of something like 10 to the minus 2, ionization degree of 10 to the minus 4, and you see the fractional abundances or contributions change. Clearly, C+ is an important coolant. In molecular gas, the situation is more complicated because we have many rotational and vibrational lines. So this cooling curve here, again, ergs per centimeter, and it needs to be folded in with the density, is very complex total contribution, but it has O2, CO, different isotopomers of CO, etc., etc., for different temperatures. So it is strongly temperature dependent. And just to show you that again, under typical conditions, at least in the high density molecular environment, the cooling is dominated by CO, but also H2 can become important. Also, the coupling between dust and gas becomes important, as you see here in this thing. Optical depth effects become important, and dynamics is important. So depending on what your velocity gradient across your cloud is, what your turbulence level is, you can have the cloud, the line escaping or not. That is important for the X factor. And Nick, I think, will be saying something about. So thermal balance would be incomplete if we just cool the gas. We also need to heat the gas. And the by far most important heating mechanism is photoelectric heating on dust. So what happens is you have your dust thing, a photon comes along, the dust gets stunned, emits an electron, electron carries some of this energy, electron collides with gas particles and gives some of this energy to the gas. So this is photoelectric heating. It could also be that the photon gets completely absorbed and then some of the energy is re-emitted in infrared. And typically both occurs, and you can calculate the typical energy gain per grain defined like that. There's something missing here. Well, by taking the total kinetic energy that the electron has afterwards by the absorption coefficient. So this gives you an effective temperature that you have. The thing is complicated by the ionization cross-section of the grains, the kinetic energy of the photoelectron, which is typically electron volts or below. The grain is often positively charged, so you need to overcome a Coulomb barrier. And there is some work function because the electron diffuses around inside your grain and loses much of its energy there. So the typical energy is something like per ionization event like 50,000 Kelvin. Not a lot, but still appreciable. So what is then now the total heating rate? To calculate it in detail is very complex. So typically what people provide is a net result. And you notice that the heating rate scales with the density linearly. So it's 10 to the minus 24 ergs per cubic centimeter per second. This is an efficiency times the density, and it couples to the radiation field. And the heating efficiency is a complex function that knows again about the temperature and the radiation field in the electrons. More detail you find in these books. I just give you here the net result so that you can take this and plug it into your computer if you want. Photoionization is the next important process. Again, the heating rate depends on the number density of the species. I need to integrate over all the photons that have energies that are above the ionization potential. I need the number of photons with frequency in the allowed range. This is then the energy that I'm left with. And this is the cross-section. And this is now simply as before the flux divided by the photon energy. It gives me the number of photons. Again, I can define an effective energy for ionization by taking the energy input by the number of events. This gives me the number, the energy input per event. Good. I can have photoheating by molecular hydrogen, which is very important and very complicated, because what happens is the photon can be absorbed in the low-lying electronic state, go up to a excited electronic state, but then there are several possibilities to come back. It can come back in the vibrational continuum of the ground state. So that means it comes back, but it has too much energy bound together, it will dissociate. 10 to 15% of the molecules do that, and this gives you right away something like 1.25 electron volts directly. We can calculate heating rates. You need to take care of photon escape probability, etc. Extinction by dust and self-shielding is important. Self-shielding is expressed by the beta escape probability, shielding by dust by the extinction. These two together give you the immediate heating rate. Now, the other thing can happen is that it excites down into a bound vibrational state of the ground electronic state, but it's still excited, and by doing infrared emission or collisions, it can hop down. And this is now, of course, much more complicated because in order to calculate it properly, you need to know the level population down here. So again, this is the equation that describes that critical density, and for a typical warm cloud in the outskirts, so extinction 0 and full escape probability, this is something like 10 to the 5 times this divided by the square root of the temperature and some exponential factor. This is very complicated to calculate. Now, I said H2 can form on dust. There is latent heat that is released as the H2 then lifts off again from the surface of the dust. It may have some kinetic energy, and this needs to be taken into account as well. You can do that by this rate. Again, there is some efficiency, how much energy is lost in the dust grain, and typically we talk about 10 to 20%. And as a side remark, this also can occur by three-body processes at high densities in the primordial universe where you have no dust. And then it's a very important heating mechanism that we need to take into account when we do first star formation. Dust-gas coupling, we have discussed before. The appropriate rate is like that. If you plug in the numbers, you end up with this term. Now, this is really a staccato of terms. You can look it up. You have heard it, should you need it. There's also cosmic ray heating. And by cosmic ray heating, you need to distinguish between primary ionization and secondary ionization. So cosmic ray heats something, releases an electron. The electron typically has very large speeds, and it can ionize again if it collides again. So this is why the ionization rate typically is larger than unity. So one cosmic ray can ionize effectively quite a number of atoms or molecules. So secondary ionization rate with hydrogen, with helium, you can plug that all in. Typical numbers are then this, 10 to the minus 27 erg per cubic centimeter per second. This is important because cosmic rays can penetrate deeply into the cloud and can provide heating rates in the highly extinct parts of clouds where other sources fail. X-ray heating, similar to the UV heating. Here is the rate. Further heating processes, turbulent heating. We have discussed the decay of turbulence for heating the galactic disk yesterday. You can also do that on a molecular cloud level. Ambipolar diffusion can provide heating if your cloud is magnetized. And gravitational heating. So I have copied this from Xander Thielen's book. This assumes you have free fall collapse. But PDV heating is more to that. You also have it in shocks. You have it in expansion. It can be positive or negative. Good. Now, the chemical reactions, I'm over time, right? Yes. So then I stop here. And we quickly do the different chemical reactions tomorrow, and then we go to star formation. And I also tell you how you solve it on a computer. So again, that was a lot, but I think it was useful to provide an overview over the different mechanisms, because usually you don't hear them in your classes. I don't know, or who has had a discussion of all these heating and cooling processes so far? Okay, a few have. Good. Should I take questions?
Yes.
There's one question.
One or two. We don't have much time. So thank you very much. So my question is, how do you, for numerically, how do you couple the chemical cooling into the hydro simulation? For example, about the time steps and also the equation of step use.
So that is what I wanted to discuss now. I will do it tomorrow. So basically, what you do is you solve the chemical rate equations using an implicit ODE solver. You need to do it implicit because you have a very stiff set of equations, and typically you need to do some subcycling. So chemistry works typically faster for these conditions than the hydrodynamics. Good. So then it is indeed a very tricky question how to couple the radiation field into that. So you can do it with full-fledged radiative transfer, which is very costly. There is a very smart and cheap way of getting at least the column densities, the attenuation of the radiation field from the outside, by using, if you have a tree-based gravity solver, as Volker has discussed, you can use the same tree that you use to calculate the gravitational forces to calculate column densities. You build a heel peak sphere around each cell, and you're looking at which column this node or other cell provides. You register that on your heel peak sphere, and you have some idea about the attenuation. So that gives you the attenuation. If you have internal sources, then you must do a diffusion solver or a ray trace solver. Yes, I think that answers your question, right?
Other questions?
Coffee.
Yes, I think so. So we break now for 20 minutes. Let's be back at 10 past